So now we prove Lemma 2, which was mentioned in the proof of Mordell's theorem. So for any given P0 on our smooth cubic curve, which is rational, which we denoted by gamma, height of P plus P0 is less than or equal to twice height of P plus kappa naught. This is a constant for all points lying on our cubic curve. So the first remark we want to make is that we can actually skip a finite number of points. Now this is because you can always take kappa naught to be greater than this difference. This is height of P plus P0 minus twice h of P. So you are taking this on this side and you are writing Pi instead of P. So you have maximum. So where Pi is the skipped point. So there are only a finitely many these Pi's. So they are finitely many. So corresponding to these finitely many points, we will only have finitely many such differences, and you can take the maximum of them as to be kappa naught, or kappa naught is greater than the maximum of these. So in fact we are not going to skip any points. We are only going to skip 3 points: the special point, P0 itself so as to avoid duplication formula, and minus P0 because we are again skipping the special point. So these 3 points will not be considered, but then you can always put it in the formula and find corresponding kappa naught so as to satisfy this inequality. So let us now prove this inequality. So we are going to assume 3 things and then prove this lemma and then prove these 3 things. So the first is, so say our point P here, this is given as x comma y. So this is a rational point on the curve. So that is, both x and y are rational numbers. Then we can show that x is equal to m over e square and y equals to n over e cube, where m and n are integers and e is a positive integer. So this we have to show, but for now we will assume it is true. And again, this is in the minimum possible form. So greatest common divisor of m and e is 1, and greatest common divisor of n and e is also 1. So you have done all the cancellations. So number 2 is height. So you know that height for a point Pxy lying on our cubic curve is always the height of the first point. So this is what we have defined the height as. So always you talk about the height of the first point. So height of this point P is actually maximum of this point. So maximum means maximum of m and maximum of e square. So maximum of m and e square, because you always consider height of the first point. So this is our definition of height. Then we can show that for this number n here, this is also has a bounded height. So n is some k times, or some constant times hp 3 by 2. So this height was here, this becomes hp 3 by 2 for all points x and y lying on the curve. So these points x look like this, which we have copied here, and y looks like this, which we have copied here. Number 3, which we also have to show, is that we add 2 points just using the chord tangent method. So this P plus P0 is a psi and eta. So this psi will be of the form a n e b m square. So obviously it will be in the form some ax and y. So you have to have some x and y here. So these x and y are replaced by m and of this form, m by e square and n by e cube, and that's why you have, instead of x and y, you have n, e, and m squares. So this also we have to show. But this is how your psi will look like. You have a n e plus b m square cme square de4 divided by em square fme square plus ge4. So for now we assume that this is true. Now this psi might not be in lower terms. There might be some cancellations, but this is not going to really matter in terms of height, because after you do the cancellations, the height will only decrease. So you know that height of this psi is nothing but maximum of absolute value of numerator, that is absolute value of this, and absolute value of denominator. So maximum of either absolute value of this or this, whichever is maximum, you pick that, and that is the height. And this denominator we are saying here. So absolute value of denominator is here. So let us now first focus on the absolute value of the numerator. So that is absolute value of this. So this we are writing is here. So obviously this is less than or equal to, you take this absolute value inside, you have a n e absolute value of bm square, absolute value of this, absolute value of this. Now focus here. So this e square is obviously less than equal to h of p. So our first, this e square is less, so e is less than equal to h of p to the power of half. And we are saying that n, absolute value of n is less than khp 3 by 2. So when you do ne, you have kh 3 by 2 times 1 half. So a and e will become akhp square. That's precisely hp square here, and you have ak here, and similar for everything else. So you have bm square, you know, m is less than equal to h of p, so m square is less than equal to h square p. So this is hp square out, absolute value of p is here. Now you have me square, again m is less than hp, e is less than hp half, but we have square here, so e square is less than h of p. So these two multiply, you have h square, which comes out, c remains here. Again you have e4, so you see e square is less than equal to h of p, so e4 is less than equal to h square. So again h square comes out, d remains as such. So this is it. Similarly for denominator, you take absolute value of this here, absolute value of this here, absolute value of this here. Again you see m is less than hp, so m square is less than h square. So this h square comes out, e remains here. Now me square, now m is less than equal to h, and e square is again less than equal to h. So me square is less than equal to h square. So again h square comes out, we have absolute value of f here. Then you have e4, e square is less than h, so e4 will also be less than h square. So again this entire thing is coming here, e square is less than h of p. So we have this value for numerator and denominator. So height is maximum of absolute value of numerator and denominator. So our height, this is less than equal to maximum of numerator or denominator, but our numerator and denominator are again less than equal to this. So this entire thing we are copying right here, and this entire thing we are copying right here, and you see hp square is common, this we keep outside. So just using this inequality right here along with these inequalities. Now this small h here is nothing but log of this h. So start taking log. So take log of this, you get here. Take log of this, you get here. Take log of this part, you get twice hp, and now kappa naught is remaining. So you get twice hp plus log max of this value. So this log max, just taking log of this now. Taking log of this you say is kappa naught, so plus kappa naught, because this is multiplication here, will become addition. And this is precisely what is our result which we needed to prove, as you can see here. So the only thing now left to show is 1, 2 and 3. So now we have to prove part 1. So x is equal to m over e square and y is equal to n over e cube, and greatest common divisor we have to show is 1. So we start with easy thing. We start writing x as m over m and y as small n over capital N, and making sure they are already in the lowest terms. And then we will show m is e square and n is e cube, so that this condition is satisfied. So this is it. So obviously there's nothing else to do other than substituting it into our cubic curve. So you substitute it in, so y becomes this n square over n square here, x cube is cube of this right here, square of this right here. Now you have to clear the denominator, so you multiply throughout by n square m cube. So you multiply here by n square m cube, this cancels out, you have m cube here. So here again you multiply by n square m cube, this will cancel out, so you have n square here. Again you have n square m cube. Do the cancellations, this is what you get. Again you have this n square m cube. Here also you have n square m cube, n square m square m. So yeah, there's nothing much to be done. Clear the denominators. So now we start seeing the first thing, that n square divides m cube n square. So see, n square is right here, n square is also here, n square is here, n square is here. So this entire side is divisible by n square. Therefore n square also divides this, and that's precisely what we have said. N square divides m cube n square. But you have already seen that greatest common divisor of small n capital N is 1. So the only thing possible is that n square divides m cube. Now for the converse, we have to show that m cube divides n square, and this will go in 3 steps. So first notice there is m here, so this term is divisible by m. There is m square here, so this term is divisible by m. This is divisible by m, and this is divisible by m because there is m cube here. So it has to be the case that this is also divisible by capital M. So that's what we write here. Capital M divides n square m cube, but the small m and capital M have no common factors as we started with here. So it has to be the case that m divides n square. So now m divides n square, that means there is a factor m sitting right here. So there was already an m here, and there is a factor m sitting here. So now this entire term has a factor of m square. So again, n square is divisible by m, so there is m sitting here. So this entire term is m cube. Now again there is a m sitting here, so now you have m4 here. So now you see this maximum factor here. So here already there is m cube. Maximum factor is m square. So this m square divides here because there's a cube here. It divides here because there are 3 factors here. It divides here. So it has to be the case that this m square should divide this n square also. This n square already has a factor of m, but now it is also divisible by m square. So this m square is now dividing n square m cube. So m square is dividing n square n cube. So that has to be the case that n square divides n square because small m and capital M have no common factors. So this implies that m divides n because m divides n square, and m square also divides n square. So now we have m square divides n square. So this n square actually has a factor m square in here. So this m square factor is here. So there is an m square factor here in n square, but there is an m here. So you multiply these two, you get m cubed. There's an m square factor here now because m square is dividing n square. So m square multiplied by m square, you have m4. So again you have a m square factor sitting inside n square because of this result. So n square multiplied by m cube, you have m5. Again you have this m cube factor which divides here, divides here, divides here. So it has to be the case this m cube divides here. So m cube divides n square m cube. So this implies that m cube divides n square because capital M and small m have no common factors. So what we have shown? We have shown n square divides m cube, and we have shown that m cube divides n square. So it is the case that m cube is equal to n square. Also we have seen that this m divides n. So what you do is you set e is equal to n actually divided by m. So whatever division there is. And that is it. Now you square it. So e square is equal to n square over m square. But now n square, instead of n square, you write m cube. So you put m cube here. So m is equal to e square. So instead of m, you have e square. So m over e square. So this first part is done. Now you cube this thing. You get n cube over m cube. But now instead of m cube, you write n square here. So you get n here. So n is equal to e cube. So this is e cube. So you have n over e cube. So the first part is done. So we have shown that every rational point on the curve can be written as x and y, where x is m over e square, y is n over e cube, and they have no common factors. M and n are integers and e is a positive integer. So now we prove that this height of the point, which is obviously max of m e square, that is height of the point on the curve, is always you talk about the height of the first point here. So we show that this n is also bounded. This is k hp 3 by 2 for all points x and y on the curve, where x is given like this and y is n over e cube. So first notice that once we cleared the denominators in the previous slide, we had a term like this, and you know that this is, this is capital M and capital N was E cube. So M cube is E6 and N square is also E6. So now you can multiply this throughout and you will get E12 here. Then you cancel out E6. You will get this term here by cancelling out E6. Anyway, it is non-zero, so you can cancel it out. So you can cancel this out. So you will get this term. So obviously there is some e's here also, here also. So here you will get some e will remain b e4m, and here you will get a e square m square. So now we start taking absolute values. So absolute value of n square is less than equal to, you just taking absolute value of each of these terms. So notice that this m here is less than h. So m is less than h. So this implies that m cube is less than h cube. So that is right here. Then you have this, you don't worry about the a, which is a constant, you take it, but you know that from here that e square is less than h and m is less than h. So you have m square is less than h square from here, and from here you have now e square m square is less than h cubed. So e square m square is less than h cubed. So that's what we have. Finally you have again m here and e4 here. So e square is less than h, so e4 is less than h square. So m e4 is less than h times h square h cube. So again you have h cube here, p remains as such. Again c remains as such. You have e square is less than h, so e6, raise both sides to the power of 3. So this is also less than h cube. So you take this h cube as common. So you get 1 plus absolute value of a plus absolute value of b plus absolute value of c times h of cube, the cube of h. So this, now you take square root because you have a square here. So get rid of this square, take the square root. This 3 becomes 3 by 2. This is precisely this, and this term we take as k. So this is our k. So finally for the third part, we have p plus p0, we are writing as psi and eta. So this psi we are saying is of this form. So how do you obtain this psi? So this is the formula for psi which we obtained by the chord tangent method. So this is written as m square minus a minus x naught, where m is y minus y0, x minus x0. M is just nothing but the slope of the line joining points x, y, which are the coordinates of point P, and joining this with x0, y0, these are the coordinates of point P0. So that is what you plug in this into m right here. Take the common denominators, you have something like this. So in this term you will have y square coming here, you have x square coming here, but this x square will get multiplied by this to get x cube. So you will have y square minus x cube. But this is our curve, y square minus x cube is equal to ax square plus bx plus c. So you get rid of this y square term and x cube term. So the only thing now will be remaining is terms in y, terms in x square, x, and bunch of constants which consist of a, b, c, and this point x0, y0. So we will have this ay bx square plus cx plus d over ex square plus fx plus g. And then you can clear all denominators because these are just rational numbers to get integers a, b, c, d, e, f, and g here. Now for y, you plug in n over e cube. For x, you plug in m over e square. So this entire thing, you do the cancellation and everything, this comes in n and e and m and e. So this is what this becomes, and this is precisely our formula right here.